If you want to take to the skies or fly to Mars, you're going to need a machine to get you there. Humans dreamed of taking flight for thousands of years, but it took special tools, techniques and materials to make it possible. It took aerospace engineering. We've been able to accomplish some remarkable things since machines have given us the power of flight. Astronauts visited the moon in less time than it takes to cross the Atlantic by boat, and my direct flight from LA to Missoula takes less time than it takes to drive across LA County. We've been able to do these things because of aerospace engineering, the field dedicated to designing and building machines that fly. It's broken down into two main parts: aeronautical engineering and astronautical engineering. Aeronautical engineering is focused on making aircraft, like gliders, jets and helicopters, while astronautical engineering builds spacecraft, like probes, satellites and spaceships. Both disciplines made enormous strides in the 20th century, thanks in part to the Cold War conflict between the US and the Soviet Union. That rivalry gave us the race to land on the moon, as well as advancements in jet propulsion, radar, material science, and so much more. Today, nations still compete, but so do private companies, and the goal isn't just getting back to the moon, but making it to Mars. It's not only a good headline. If we've learned anything from the space race, it's that competition drives innovation. The rocket company SpaceX plans on sending people to Mars as early as 2024, and to make that happen, you need a lot of innovation. But whether you're sending people across space or just flying around in the atmosphere, you're going to need to know some basic flying principles. For atmospheric flight, the critical one is lift, and the most basic form of lift is buoyancy. Buoyancy works because the atmosphere has what physicists call a pressure gradient, meaning that air pressure gets a tiny bit smaller for every little bit higher you go. The difference in those pressures creates a small upward force which can push an object up if it's light enough. That's lift. The earliest form of flight, hot air balloons, uses this principle. That big ball of hot air is pushed up because it's lighter than the surrounding cooler air, and it pulls its passenger along for the ride. If you want your balloon to be stationary, what engineers might call an equilibrium, then the sum of the forces should be equal to zero. That means that the weight of the gravity pulling the balloon and the gas inside downwards needs to exactly balance out the force of the pressure gradient pushing up. But balloons are pretty impractical for most applications. They're so dependent on the surrounding environment that things like changing weather conditions can make it hard to precisely steer or even land in one. To fly more effectively, you need a propulsion system or something that pushes you forward. A propulsion system usually consists of a power source and a propulsor, which is something that can convert power into forward motion. There are three main propulsion systems that you'll use as an aeronautical engineer: a heat engine with fuel, an electric motor with batteries, or an electric motor with solar cells. The goal with any of these systems is to provide enough thrust to overcome the drag of the aircraft. For commercial airplanes that do a lot of consistent travel, you'll want to keep the engine efficiency high and fuel usage low so that you're not burning a hole in your wallet. For something like a fighter jet where speed is key, you'll need more thrust to accelerate quickly, which means that engine efficiency might go out the window. Most modern planes rely on the jet engine, which has 5 core elements: an inlet, compressor, burner, turbine and nozzle. The inlet brings air into the engine, and that air is fed to the compressor. The compressor then increases the pressure of the incoming air before it enters the burner. At this stage of the engine, that high pressure air is combined with fuel and burned. This creates hot exhaust gas that's used to turn a turbine, which produces thrust as that air is passed through the nozzle. Finally, the nozzle acts as your propulsor, pushing the plane forward. Now, there's a few important things to consider here. You need to make sure that you have a sturdy inlet that can operate efficiently, meaning that it can bring in enough air to the compressor for your aircraft's entire flight. When you're flying at low speeds, your compressor can handle pulling air into the engine itself, but at higher speeds, a good inlet design allows you to have better maneuverability without disrupting the airflow to the compressor. You also need to design your engine with materials that can withstand a lot of heat. For instance, the blades in your turbine can experience temperatures of several hundred degrees Celsius. You need to make them from special metals that can withstand that heat, like a nickel-based superalloy, or add a system to actively cool the blades. If you decide to cool them, you'll need a hollow design so that you can pump cool air into the blades and out through small holes on their surface to keep everything cool. Put that all together, make sure you have a good nozzle to act as a propulsor, and you'd have yourself a quality propulsion system. Now, that will get you pretty far here on Earth, but think about traveling to space and you're going to have to deal with a whole other slew of challenges. And the biggest one is actually you. You might think that technological limitations are what's stopping stopping us from travelling the stars. And that's certainly part of it, but your greatest obstacle will come from the human body's difficulty in adapting to the challenges of deep space. Our bodies just can't flip a switch and suddenly adapt, so you'll need to build ships that can mimic an Earth-like environment. Some aspects, like creating a breathable atmosphere, are pretty easy. Others, like dealing with weightlessness, are much harder. One thing we don't have yet is artificial gravity. Gravity affects everything from the development of your bones and muscles to how easily your heart pumps blood through your body. Without it, astronauts in space experience issues like weaker muscles or blurrier vision after just a few days. One way to deal with this, at least in theory, is to take advantage of the apparent centrifugal force and create a spacecraft that spins. This could effectively mimic gravity in a similar way to how water stays in a rapidly spinning bucket. Space is also full of radiation, which can increase the crew's risk of cancer and even hurt the ship. Long-term exposure to radiation can severely damage onboard electronics, causing short circuits and corrupting memory. So if you don't want your design to get fried in space, you need to build it to withstand that radiation. Using insulating materials for computer chips instead of the usual silicon will help. So we're designing electronics to have external shields made out of things like lead. That will make the overall size of your system larger, so you have to factor that in too. And that's just space itself. There's even more to consider once you start talking about dealing with the atmospheres of other planets. Take a look at Mars and you'll find an atmosphere about 1% as dense as Earth's, and a temperature that ranges from minus 125 degrees Celsius in the winter to about 20 degrees Celsius in the summer. All things that your designs need to be able to handle if we ever have hopes of travelling or even living there. But before you go off and try and colonise another planet, it's good to start with a simpler mission like designing a satellite that doesn't have all the problems of needing an astronaut on board. Satellites have three main elements: the payload, the bus, and the launcher. The payload is all the equipment that performs the satellite's main functions, like receiving telecommunications or processing and sending data. The bus refers to the systems and structures that provide functions like power, protection, stability, and orbital control, which all allow the payload to perform its intended mission. The launcher, or the launch vehicle adapter assembly, is the connection between the bus and the rocket that boosts the satellite into orbit. All of these parts need to come together in the design of your satellite, and you better make sure all your math is right, because a simple calculation mistake can be devastating, both in terms of human life and in the cost of all your equipment. Back around the turn of the millennium, NASA lost a $125 million Mars orbiter just because of a mix-up of units. NASA's team was using metric units, while the manufacturer was using English ones, ultimately throwing off the orbiter's calculations and causing it to burn up in the Martian atmosphere. There's one last special kind of spacecraft you might need to design: a spacesuit. You see, a spacesuit isn't just a set of clothes that you wear in space. It's basically its own human-sized ship. It protects an astronaut from getting too hot or too cold, provides them with oxygen to breathe, and can even store drinking water. And they have those gold-lined visors that shield their eyes from the super bright sunlight of space. And the suit's tough exterior provides protection from space dust, which can actually be really dangerous when it's moving around faster than a speeding bullet. You can't beef the suit up too much though, because astronauts still need to be able to move around effectively. Conserving energy is also important since the food options are a little more limited up there. That's why engineers are always trying to come up with better spacesuit designs, like NASA's Z2 advanced prototype. The Z2 uses advanced composites to achieve a lightweight, highly durable suit that could withstand long-duration missions in harsh environments, like the one found on Mars. Whether it's SpaceX, NASA, or someone else, whoever plans on getting to Mars will need spacesuits like these, and a good spaceship. But with the right engineering practices and a little luck, there's a good chance that one day we'll be a multi-planetary species. Today we learned all about aerospace engineering and its two main fields of aeronautical engineering and astronautical engineering. We applied the concepts of lift and buoyancy to flying and found out how a propulsion system is more effective than something like a hot air balloon. Then we learned how managing the human body in space is one of the biggest challenges that aerospace engineers face. Finally, we learned what goes into making a good spacesuit. I'll see you next time when we talk all about computer engineering. Crash Course Engineering is produced in association with PBS Digital Studios, which also produces Space Time. Explore the outer reaches of space, the depths of astrophysics, and anything else you can think of beyond planet Earth. Check it out in the link in the description. Crash Course is a Complexly production, and this episode was filmed in the Dr. Cheryl C. Kinney studio with the help of these wonderful people, and our amazing graphics team is Thought Cafe.